In this video, I want to look at gravitational potential energy. You lift a book 3 times, demonstrated here. First, you lift it 10 centimeters, then you lift it half a meter, then you lift it 1 meter off the ground, each time bringing it to rest. What was the net work done on the book each time? And the answer is 0. The net work on an object is equal to its change in kinetic energy. If it started at rest and ended at rest, then the net work on the book is 0. But does that mean these situations are exactly the same? Of course not. If you were to drop them, you would get very different results. We know that dropping something under free fall, it will attain a speed of the square root of 2 times g times the height at which it was released. So the speeds these books will have right before they hit the ground will be considerably different. And from that, if we assume the mass of the book is, say, 1 kilogram, they each will have significantly different kinetic energies as well. The one dropped from 1 meter will have 10 times the kinetic energy of the one dropped from 10 centimeters. In fact, if we were to substitute this into the kinetic energy, we find that the kinetic energy that the book has right before it hits the ground is proportional to the height at which it was released. So the book that was raised higher was able to have significantly more kinetic energy, yet the net work on the book was 0, just like the one raised 10 centimeters. How is that possible? And the answer is, by doing work, lifting things against the force of gravity, that energy was stored inside the system of the book and the earth. And that system, having stored the energy, has the potential to release that energy to do work later. Let's take a closer look at how this happens. So you start not with a single object, but with a system of objects. In this case, we have the book-earth system. And this system interact via Newton's third law force pair. The Earth exerts a gravitational force on the book exerts a gravitational force on the Earth. Now you, external to this system, go in and you change the position of the object relative to the agent. Note that in doing so, because the objects are interacting, the Earth is also doing work on the object you are moving. Work comes from a force acting over a distance, and since the Earth is acting on the book and it's moving, the Earth is also doing work. The amount of new energy stored in the system after you move the book is equal to the negative work gravity did when the system is changed. Now that might seem a little confusing. Why would it be negative work if it's being added to the system? And the point is, when you're lifting the book, you are in fact adding energy to this system. The point is, how do we calculate that? And you can calculate that because the amount of energy you added to the system in this way is exactly equal to the negative work gravity did to the object when the system was changed. We don't know much about the force you used to move the book. That stored energy is called potential energy. It has a label U, and it is an energy of position. Just like we had kinetic energy was an energy of motion, the potential energy depends on the configuration of interacting objects. And we have a simple expression to find changes in gravitational potential energy. The change in gravitational potential energy is equal to the negative work done by gravity on the object that was moved. Let's do a quick calculation of that potential energy difference. The gravitational force is a constant. To come up with a mathematical representation of it, we do need a coordinate system. I've decided to put my 0 here at the surface of the Earth and positive y up. With that coordinate system, the mathematical representation of the force due to gravity is this. It has a magnitude of the mass times the acceleration due to gravity, and it's pointing in the negative y direction. The work then, because gravitational force is a constant, is just that constant force times the displacement vector. An arbitrary displacement vector can be written as this: the x displacement times I hat, the y displacement times j hat, and the z displacement times k hat, where delta x, delta y, delta z are just the components. So the change in potential energy is equal to the negative work done by gravity on the object that moves. I can now calculate that work from this dot product, and I get negative mg times delta y. Only the y components show up in my answer because there is no x component or z component for the force due to gravity. And then the result is positive because I have a minus sign from this component and I have a minus sign there. So this represents the change in gravitational potential energy whenever an object is moved near the surface of the Earth. I could write that, regardless of my coordinate system, this way. The change in gravitational potential energy for any object is its mass times g times the vertical displacement, and only the vertical displacement, where up increases the potential energy. So regardless of which way your coordinate system is pointing, you're increasing your potential energy going further away from the surface of the Earth. So if I were to calculate the change in gravitational potential for lifting my book each of those 3 times, I get these values, which were exactly the kinetic energy I received once I dropped the book. By lifting the book, I stored that amount of energy in the system, which was then released and turned into kinetic energy after I dropped it. The final point is that only changes in kinetic energy matter. There is a zero of kinetic energy when the speed is 0. However, for potential energy, we only calculate changes due to the work done by changing the positions of the objects.